All right, time for Chapter 5. We're going to get down to some of the concepts specific to cloud formation and precipitation. And when we take a look at the atmosphere, there are 4 ways that we can force air to rise. We can heat the surface, and then that heats the air above it. Hot air rises, like your hot air balloon. So a heated surface forces air to rise. We can also force air up a mountainside. That's forcing air up over topography, and that is known as orographic lift. The 2 other ways we can force air to rise is over an area of low pressure or over a frontal boundary. And frontal boundaries are considered to be elongated areas of low pressure, so both of those methods really are forcing air up over low pressure. So your 4 ways to force air to rise: over a heated surface, orographic lift, over an area of low pressure, and then over a front. So what actually happens when air is forced to rise? As you go up in the atmospheric pressure goes down. Gravity pulls most of the molecules in the air closer to the surface, so pressure is highest at the surface. As you go up in the atmosphere, that pressure decreases. Pressure is highest on the ground level, and then pressure is lowest up at the edge of space. And so as you go up in the atmosphere, there's less pressure pressing down on things, including parcels of air. So that parcel of air with less pressure pressing down on it will expand. As it expands, some of the energy the air molecules have are used in that expansion, and that air cools. Now, the opposite happens when you force air to sink. It warms by compression. As that parcel is forced to sink, the pressure in the atmosphere gets higher. It presses in on the parcel. It causes it to sink, and that causes the molecules to move more quickly as they bounce off a smaller and smaller parcel. The faster moving molecules means warmer air. So air that is forced to rise cools by expansion. Air that is forced to sink warms by compression. So what happens when air is forced to rise? The temperature of the air cools to its dew point. Once it reaches its dew point, then we know that the relative humidity has increased to 100%. 100% relative humidity means that that air is saturated. If you continue to lift the air, some of that water vapor, some of those water vapor molecules that are in that parcel can no longer hold as much water vapor because it is colder, and so some of those parcels have to go somewhere. What happens to them? They condense into water droplets. So the water vapor that is in solution in the parcel comes out of the solution because the air can no longer hold as much water vapor because it's colder, and you get condensation into water droplets. Remember, cooling ends up with condensation. So condensation occurs in the form of cloud droplets, and then in the atmosphere, those cloud droplets are clouds. Down by the ground, they're going to be dew, frost, or haze. So the lifting of air causes it to cool, and that causes cloud formation and eventually precipitation. So this is the way it looks at the surface. We're talking about high pressure and low pressure. And in the case of low pressure, an area of low pressure at the surface causes the air around it to move toward the low pressure in a counterclockwise rotation. Think of it as like a bowl in the atmosphere. That low pressure is the depression or is the bowl, and so air slides down into that bowl and moves toward the low and moves counterclockwise down into the low. So air moving inward is said to be converging. It's running into itself, and mass can't occupy the same space at the same time. So as that air converges, it can't go into the ground. It's forced to go up. So air moving inward towards an area of surface low pressure piles up and is forced to rise over the area of low pressure. As a parcel is forced to rise, it will expand. Expansion occurs because pressure decreases with height. The molecules use up some of their energy in that expansion, and that results in cooling. As air cools, its relative humidity increases until saturation, then cloud formation, then precipitation. So low pressure basically results in foul weather. Low pressure causes air to rise, and that's where you're going to get cloud cover and precipitation. So low pressure results in foul weather. Now, conversely, high pressure does the opposite. High pressure causes air to sink. An area of high pressure at the surface causes air around it to move outward in a clockwise rotation. So air is sinking down because the air pressure is higher. It's sinking down. Air moves outward and diverges away from the area of low pressure. And literally air sinks down onto the area of low pressure. So as a parcel of air sinks in the atmosphere, it compresses and warms. As it compresses and warms, its relative humidity is going to decrease. So in the atmosphere, if a parcel of air is in a cloud, and it's forced to sink, and it warms and relative humidity decreases, then you're going to see evaporation at the surface. You're going to see evaporation of fog. So high pressure results in fair weather. Low pressure results in foul weather. High pressure results in fair weather. So the formation of rain. Once our low pressure has cooled the parcel until it reaches its dew point, once it reaches its dew point, saturation, further lifting causes condensation and cloud droplets. You can see that those typical cloud droplets are significantly smaller than a raindrop. So how does a cloud droplet become a raindrop? Well, it has to grow on an order of almost 1 million times. So there's two main ways that cloud droplets turn into rain droplets, and that's the collision and coalescence process, the Bergeron or the ice crystal process. And you can get the details on both of those in your book and in the lecture as well. Of course, once cloud droplets become raindrops, they fall as precipitation. So how does this look at the surface with regards to fronts? I said that fronts are areas, elongated areas of low pressure. Winds diverge along fronts as well. So air masses are large, the size of half a continent. Air masses are large areas of air with similar properties of temperature and humidity. Fronts are the transition zones between air masses of different densities. And the reason why they have different densities is because of the differences between temperature and humidity. If it's a warm, humid air mass, it's going to be less humid than a cold, dry air mass. A warm, humid air mass will want to rise. A cold, dry air mass will want to sink. So density differences are due to the different properties of temperature and humidity. Fronts are those elongated areas of low pressure on which winds also converge and want to rise. So look at the top picture. The cold air is coming in from the north. The warm, moist air is coming in from the south. The air converges along that cold front, and the warm air is forced to rise. In the second picture down, that's a warm front. The advancing warm front is warm, moist air. It comes into some cooler, dry air coming in from the north, and in that case, the warm, moist air flows up over the cold air and is forced to rise. And you see the same thing in that lower picture with your area of low pressure, the surface, your cold front extending from the low pressure, your warm front extending out of the low pressure. That little corner of that whole little low circle that is the southeastern states, that's known as the warm sector of that cyclone. That low is a cyclone. And so cold, dry air is coming in from the northwest. It's converging with warm, moist air along the cold front coming in from the south and southwest. And then that south-southwest wind is converging at the warm front on the cold air to the north. So in both cases, the warm front and the cold front, air is forced to rise. So fronts are named for the type of air that is advancing with cold fronts having cold and dry air advancing under warm, humid air, and warm fronts having warm and humid air advancing over colder air. Rising air cools to its dew point, further lift forces condensation and cloud formation, and eventually you get precipitation.